So here we go again. Hello and welcome to the Daily Space for Thursday, May 31st of 2018. I am your host, Dr. Andreas Plazas, stepping in for Dr. Pamela Gay. And as always, we are going to bring you a roundup of today's news from space and astronomy. Today we're going to talk about three stories. One of them is about finding exoplanets using our own planet. The other story is about galaxy collisions, and finally we're going to discuss a little bit about a possible dark matter candidate, an electrically charged particle, to explain observations of the early universe. So let's begin. So our first story is about exoplanets, and as you know, the look for exoplanets that look like our Earth is one of the main questions, and many of the is ranks high in the agenda of exoplanetary scientists. However, this is a little bit more complicated than just finding a planet that lies within the habitable zone. You know, that zone that we call the Goldilocks zone, where the planet is not too close or not too far from its host star in order for it to have liquid water. There are other factors such as the planet atmosphere, and even in daily space a few days ago we were talking about the ellipticity of the planet. Being another important factor. But well, today in the paper I would like to talk about the authors are actually considering a slightly different approach, and they are considering the possibilities of direct imaging of an exoplanet. Where I should say that we're still far from having an actual image from an exoplanet, a resolved image of an exoplanet. But one of the things that we can do, and actually what they do here in this paper, is we can use our own planet Earth as a proxy exoplanet. And so the authors actually use multi-wavelength observations from the Deep Space Climate Observatory, and they want to figure out what we should be looking for in other exoplanets that are supposed to look like our own Earth. This observatory is largely used for space weather monitoring, but it has an instrument that is called the Earth Polychromatic Imaging Camera, or the EPIC camera, that is taking pictures of the sunny side of our planet in 10 different wavelengths, ranging from ultraviolet to near infrared. And this instrument has the advantage over many other Earth observing missions in that the data span a long period of time. The authors have used data that have a span over 2 years. And the advantage of that is that you can look at how these images in every wavelength they change with time in 2 years, on periods ranging from on time scales ranging from hours or even 2 years. Now we have 2 years of data. And what do they find? Well, do you expect to find? What do we expect to find when we look at the Earth in different wavelengths? Well, we expect that the reflectance of the different surface elements, such as the ocean or such as the vegetation, changes with wavelength. So, for example, the ocean, it reflects most in the blue or green wavelengths, whereas vegetations, it has a more reflectance in the near infrared wavelengths. So we want to analyze the differences in reflections between the short wavelengths and the long wavelengths, the red wavelengths and infrared wavelengths. And then at the same time, we want to study these changes over a period of time. So, well, of course, there are assumptions, there are complications, and one of the obvious ones is that this camera, the EPIC camera, has a resolution of 12 kilometers by 12 kilometers, which is a superb resolution, and we do not have such a resolution for an exoplanet that could be like many light years away from us. So, well, but you can do is to try to bring that data to what it would look like to a data from an exoplanet. So they actually, to simulate the imaging of an exoplanet, the authors take an average of the data with good resolution into just 1 pixel. And then they look at the time evolution of the signals in each wavelength. So of course we're losing a lot of information when we're doing this average, but at the same time we still have the information of the changes with time and the changes with wavelength, and then we expect to compare these averages with what we actually would expect to observe from an exoplanet. So one of the techniques that the authors use is what is called Fourier analysis. So just in very general terms, any wave, any signal, for example, any signal from a song or from my voice, uh, you can, or from the image of an exoplanet, right, in different wavelengths, you can express the signal as the infinite sum of very simple signals, of a very simple oscillations that we call sinusoidal waves. So when you use Fourier analysis, you are actually trying to figure out how, if you have a complex image, for example, that have many wavelengths, you are trying to figure out what the components simpler signals are, like at which wavelengths do they have and which amplitudes do they have. So if we apply Fourier analysis to this kind of data, the authors actually can find different structures that have certain periodicities. So for example, they are able to find a peak at 24 hours and a peak at 365 days and another peak at 12 hours. And then you can, in the Earth, it is obvious for us that these peaks are associated with, of course, the daily rotation of the Earth or the yearly translation of the Earth. And we expect to use the similar technique to find for periodicities in an exoplanet when we have this imaging. So just to wrap up, as I said before, in practice, directly imaging exoplanets is very challenging, and there's still a lot of work to do. So what the people do actually study the atmospheres of exoplanets, but they use a spectroscopy. What does that mean? If you have a star and then you have a host exoplanet, then the light from the star is going to hit the atmosphere of that exoplanet in front of it, and then you can study the absorption. You can measure the light and how the light is absorbed at that atmosphere, and then you can figure out if there is oxygen or what kind of components there are, or the opacity of the atmosphere um, to tell about the composition of the how thick it is actually. So we actually do that right now, and it's through a spectroscopy. But in this paper, we're toying with the idea of actually imaging, or actually having a picture of an exoplanet and what you would expect to find by looking at the Earth, which is what we have right now. So yeah, that was our first story. And the next story I wanted to talk about is about an image from the Hubble Space Telescope. That just give me a second, everyone. That actually looks like an image of a single galaxy, but is representing the site of a violent clash between two spiral galaxies. So okay, this is an image from the Hubble Space Telescope. For those of you who can look at it right now, let me see. Yes, you should be able to look at the image. It is called NGC 3256, New General Catalog 3256, and it is actually the relic of a collision between two spiral galaxies, estimated to have occurred about 500 million years ago. So this object is located about 100 million years away from us, not super far, still far, but not super far. And those extended tails, that are sprawl around this object, they are thought to have formed, as I said, about 500 million years ago during the initial encounter between these two spiral galaxies. And what is this interesting? Because we think that this is one of the mechanisms that structure in the universe forms, right? We are expecting one of the mechanisms in which the large-scale structure of the universe is through merging of galaxies. And what happens when two galaxies collide? Well, it turns out that there's a lot of empty space between one star and the other. So individual stars, they rarely collide. So however, the gas and the dust between the stars, they actually interact. And this has a lot of very interesting results. because this is going, for example, this is going to trigger a large amount of what we call a star formation, and then you can tell that a lot of new stars are going to born into groups and clusters of stars that have been interacted with this dust, the interstellar dust. This type of galaxies actually shine mostly in the shine most brightly in the far infrared. And this type of galaxies, because of this radiation, is what we call a luminous infrared galaxies. They are very good traces of the large scale structure of the universe, because you can use infrared cameras, and then you can find a lot of these objects, and then you can trace the cosmic web using these very luminous infrared galaxies. Um, the researchers in this press release, in this article, they actually found out that there's molecular gases spinning around two distinct nuclei. And the cool thing is that to first sight, the nuclei are not actually very apparent, but because one of the nucleus is actually obscured, and you can only see it in the infrared and other wavelengths such as the radio and the X-rays, other wavelengths in addition to the visual wavelengths. And in a few, what's going to happen with a galaxy like this? So we can know, because of the theories of galaxy formations, that in a few 100 million years time, their nuclei will also merge, and the two galaxies will likely become one galaxy, one large elliptical galaxy. So this is a very interesting cosmic event, because it brings to my mind, for example, the collision between two galaxy clusters. Here we're talking about galaxies, but in the past we have also seen the collision between two galaxy clusters. And one of the most famous clusters that has collided is what we call the bullet cluster, where you could actually, I just mentioned in this news that you could actually, most of the stars are not going to collide, but the gas, the interstellar gas is actually between the two clusters of the two galaxies actually interact. But what is particular about this bullet cluster that I'm talking about is that is providing with one of the most direct evidences of the existence of dark matter. And this is going to bring us into the next story of the day. So just to recap a little bit, the standard cosmological model of the universe calls for a component we call dark matter, another component that we call dark energy, and this dark sector of the universe is about 95% of the total contents of the universe. We don't know what these two components are. Dark matter is about 25% of the component of the total component of the universe, and it's about more than 80% of the total matter in the universe. So we have the regular matter that we're all made of, the stars, the galaxies, and then we have the dark matter. And one of the candidates of dark matter, people think that they are elemental particles that we actually haven't detected. But one of the defining characteristics of dark matter is that it does not interact with electromagnetic radiation, and that's why it has the adjective dark. However, in this last article that I wanted to talk about with you guys, some researchers are actually proposing that a small fraction of dark matter actually is charged. So, what is this article about? So, this is an article brought to us by two researchers from Harvard University, Julian Munoz. He says Munoz, but I think it's Munoz. And his collaborator, the director of the astronomy department at Harvard, Avi Loev. And they have published this paper in the journal Nature, one of the most prestigious papers in science, and they explore the possibility that that the particles of dark matter might have a small charge, and because of this charge, these particles might be able to interact with normal matter. So the current accepted theory of dark matter is that it only interacts with other particles through gravity, through its gravitational attraction. It doesn't interact, as I said, through electromagnetic radiation. But they are in this paper. These two researchers are challenging this assumption, and well, so far you guys are going to say, well, it's just another theory, and of course, every day people come up with new ideas of what dark matter could be, and there's nothing wrong about that. But in the end, when you're doing science, you need to validate your theory with observations, right? So the interesting thing about this is that the work actually is trying to explain a recently announced result from an actual experiment. It's called the experiment to detect the global epoch of reionization signature, or EDGES. Very convoluted acronym, but well, it's called the EDGES collaboration. And actually, this project in February, the scientists from this project, they reported that they had detected the radio signature from the very first generation of stars. So this first generation of stars, they started to emit ultraviolet light, and according to the common theory, the accepted scenario, this ultraviolet light interacted with cold hydrogen atoms that was in the gas line between the stars. And because of this, these hydrogen atoms were able to start to absorb the radiation from the cosmic microwave background, which is the leftover radiation from the Big Bang, from the epoch of the Big Bang. Well, the interesting thing, what they actually saw is, or what you would expect to see, is that this absorption should have led to a drop in the intensity of the CMB during this time, of the cosmic microwave background during this time. But what the EDGES experiments, this experiment actually found or detected, is that the hydrogen gas was cooler than what is expected. They actually found that the temperature of this hydrogen gas, or the intensity of this hydrogen gas, it was about a half of what the current theory would tell it would be. So the proposers of these articles, Dr. Munoz and Dr. Loev, are actually saying that one possibility is that the hydrogen was cooled down by dark matter. How could it be? Well, at the time when the CMB radiation is being absorbed, most of the free electrons or protons that are associated with ordinary matter, they would have been moving very slowly, because that's how you can form atoms. If you have protons and electrons that are moving very fast, they are not going to be able to be bound in atoms. So we know that these particles, they would have been moving at their slowest possible speeds. And actually, from the theory of particle physics, we know that the scattering of charged particles is most effective at low speeds, which kind of makes sense. No? The scattering is the probability of interaction of two particles, no? What we call the cross-section of interaction of these two particles. So the researchers say that in their theory, that any interaction between normal matter and then a little bit of dark matter that has charge during this time would have been the strongest if the dark matter particles are charged. And this interaction would cause the hydrogen gas to cool down, because actually the dark matter is cold. That means it's not moving at high speeds. And this could potentially leave an observational signature that they claim matches what the EDGES project is seeing. So in the end, I haven't actually looked at this paper in detail, but what I would think is like, okay, it sounds plausible, but we have the usual caveats, no? As we know, like great claims require extraordinary claims require extraordinary evidence. So okay, this could be an option of what the dark matter could be, or what the characteristic of dark matter could be. But then first they would need to match the observations. They claim they matches the observation of this particular project, but at the same time, the hypothesis of dark matter turns out to be very successful in the standard cosmological model. And that's why it's part of the standard cosmological model. Because let's be clear, as physicists, as astronomers, we do not like to have to introduce in our model a new component of the universe that we have no idea what it is. Dark matter, and then we also have dark energy. That's what it is. We don't know exactly what it is, but we introduce these new components into our model, because by doing so, it actually matches a lot of the observations that that we have. And these observations, they range from astrophysical observations of the scales of galaxies, of the scales of clusters of galaxies colliding, as I said, but also the observations match the information that we get from, for example, the cosmic microwave background. If you can measure in detail the fluctuations in temperature of the cosmic microwave background, and you introduce the hypothesis of dark matter, and you change the amount of dark matter that you should have in order to reproduce these observations, it actually matches very well. So if you have a new theory of dark matter or a new theory of dark energy, or you should be able to explain all these observations on all different scales so far. And then on top of that, you should be able to make predictions, future predictions of what your theory should present when you have a new observation. That is to say, we want our theory to be falsifiable. If you don't have a falsifiable theory, your theory is not scientific. Okay, well, this is what I wanted to bring you guys today. Thank you for your attention, and sorry again for the technical problems that I had at the beginning. But I'm gonna look at the chat right now and maybe see if you have any comments or any questions. Let me see. Where is my chat window? Somewhere. Right here. Okay. What is it? Oh. Okay. Hello, everyone. So one of the questions is, do you mean dark matter or dark energy? I had an explanation like that for dark energy. Today we're talking about dark matter. But then in the end, I was talking about the general principle of being able to explain observations. That's general in science, and that applies both for dark matter and dark energy. For example, we think that dark matter is a fundamental particle that is not moving at high speeds. That's why we call it cold. That doesn't interact with electromagnetic radiation mainly. And we haven't found it yet, but if we introduce that hypothesis into our theory, then that matches observation. Something analogous happens with dark energy. One of the main candidates for the existence of dark energy is that is a component with, assuming that general relativity is right, that is a component that has negative pressure and that is constant in time. The density of dark energy it should be constant in time, and this is one of the simplest hypotheses to explain what dark energy is. Dark energy is just a placeholder name, and this is what is called the cosmological constant. And the bottom line is that so far the data that we have fits this model, the standard cosmological model. Is actually, we call it the lambda Kolk dark matter model, and lambda stands is the Greek letter that we give to the cosmological constant. Again, there are theories that say, oh, maybe we need to modify gravity, maybe it's not a particle, or the theory that we were talking about today. Maybe dark matter actually has a little bit of, not all of it, but has a little bit of electric charge. So you can invoke these theories to try to explain a certain amount of observations, but the point is that right now there's a large variety of observations on different scales that should match. And yeah, one of the way of moving forward is actually getting more observations. So that's what we're actually doing. We're actually trying to find dark matter undermines directly, or trying to look for annihilation of dark matter at the center of our galaxy. And the same with dark energy. We're building a telescope like the Large Synoptic Survey Telescope that wants to get better data in order to figure out the evolution of the universe with time, and hence knowing more about dark energy, for example. Are they saying that dark matter is minimally charged or just some? They're saying actually both. Actually, I forgot to mention this. I think they're saying that it is minimally charged, that it has, in the sense that it has 1/1 millionth of the charge of the electron, so 10 to the minus 6. And at the same time, they also say that just a small fraction of the dark matter is charged. I don't know which fraction, but in the same way that throughout the history of the universe, when we had, as I was saying, we had electrons and protons that were moving very fast, but as the universe expanded and cooled down, the distribution of the velocities of the electrons and protons lowered. So a lot of the electrons and protons could be actually ended up being bound in atoms, but none of them. There was still a very small fraction of these particles that remained unbound and hence electrically charged. So they're saying that something similar maybe could have happened in this scenario. I actually haven't read in full detail the paper, but it would be interesting. Not very electrifying, then yes, that is correct. But even if it's a very tiny amount, then it could have a cumulative effect on large scales. Okay, guys. So I think I'm gonna leave you for today. Tomorrow we might have Pamela, or maybe it's me again. I don't know. We'll see. But it's probably Pamela. But well, thank you very much for watching, and this has been the Daily Space, a production of CosmoQuest, created by the Astronomical Society of the Pacific. And our goal is to put science in your brain. Do you want more content? Tonight at 5 p.m. Eastern, 10 p.m. London, and 2 p.m. Pacific, Astronomy Cast will be recording live on YouTube. And if you like this show, please give us a follow. And if you want to sustain our efforts, please consider subscribing. And yes, well, thank you very much. And the Daily Space will be back tomorrow every weekend at 1 p.m. Eastern, 10 a.m. Pacific, and 6 p.m. London. And tune in tomorrow to see what is new in space and astronomy. All right. Bye bye.